Out from Johns Hopkins University, and thanks for attending my talk. Today I'm going to be talking about our programming language using a relational algebra and executing via term rewriting. So this talk is about our relational expression language, or RXpers for short, that we have developed and are manipulated using term rewriting. Now, the reason that we have developed RXpers is that we needed an intermediate representation for the programming language Dyna. Dyna is a logic programming language that generalizes data log and Prolog and has been designed to be especially good for representing weighted programs such as those commonly found in machine learning and artificial intelligence applications. Now, the reason that Dyna is well suited for these particular problems is that all these problems only care about what we are computing and not exactly how it is computed, and our expressions allow us to accomplish this. Much like a database, we interact with a program by taking our original program, represented as a relational expression, and intersecting it with a query and further rewriting it. Once we have reached a normal form and there are no more rewrites we can apply, we have hopefully reached some form that is easily interpretable by the user. So why did we develop this new programming language and invent a relational algebra for Dyna's internal representation? To answer this, I'm going to go through a quick feature matrix of well-known tools including SQL, Datalog, Prolog, constraint logic programming, and Dyna. First, we have that all these systems support finite databases, as there always exists an option to simply loop over all the values which are contained in the database. For deductive, only the logic programming systems suffice, as they are designed to combine rules together with new facts and discover new facts in the database. To support an infinite database, the system needs to have some strategy which can avoid expanding an infinite number of items in the database, essentially early termination or higher order reasoning about the problem. Aggregation allows the system to combine the results from many different facts in the database. Here I have illustrated this as a SQL sum query. Aggregation also turns out to be necessary for making interesting weighted programs, as we'll see momentarily. Turing complete, or if this is a full programming language. Constraints, or if we support expressions such as x less than y or y less than x, and identify that this is not possible without having to identify values for x and y. Now, as you might have guessed, we would like to support all of this in Dyna. And the reason this hasn't been done before is that aggregation and infinite databases are somewhat difficult to mix. So why is aggregation and infinite relations hard to mix? So some of the aggregators that we have are logical OR, which is what is traditionally used in logic programming, as it allows the system to early stop when it has found some true value. And we have logical AND, which would check that all the aggregated values are true, or stop early in the case that a false value is found. Sum and product are also common when dealing with numerical or weighted programs. Min and max are also common aggregators. Often they require expanding all the values to select the one that is smallest or largest. However, in some cases, such as with a linear program, for example, it might be possible to exploit structure in the problem to be more efficient and find the solution. In the case of infinite expressions, we cannot enumerate all the values, as that would never terminate. This makes it hard to use any aggregator except for logical OR, which can stop enumerating values early. Despite this, there are still some infinite sets where aggregation is well defined. For example, we can represent the set of numbers greater than or equal to 5, in which case the minimum value is still well defined, but computing the sum of this set would diverge. It might also be the case that we have infinite sets of convergent sequence. As such, we need some way to be able to represent these infinite sets. To quickly convince you that aggregation is useful in logic programming, I have just a few quick examples. If you have ever written Prolog or Datalog programs, you have likely written a rule like this. In this case, for any given value of I, the rule AI will be defined if both BI and CI are defined for the same value of I. The aggregator here is the OR aggregator, which can stop once it has found something that satisfies this expression. Now we might instead want to write a pointwise multiplication, where it requires that both BI and CI return a value that can be assigned to another weight for the expression AI. If we remove I from the head of this expression and replace it with the equals with the sum aggregator, we now have a dot product, where for every value of I, we are multiplying BI and CI together and summing the result. Further note that the value of I is not restricted to be over the integers. The variable I can be any value in the language or the Herbrand universe. Also, depending on the definition of BI and CI, this could be the infinite sum. So we cannot even determine from this one rule in the program if this is a finite or infinite sum. One reason that we like Dyna is it lets us concisely define mathematical equations. For example, this single line defines a matrix multiplication. The variable I and k, which appear in the head on the left-hand side, are the same as in the body, while the variable j, which only appears on the right-hand side, is aggregated over using the sum aggregator. Again, we do not know if this is an infinite sum given this single line of code. For example, if we were to define Bij, as I have written here at the bottom, then B is defined to be an infinite identity matrix, where any time its two arguments are equal to each other, it takes on the value 1, otherwise it takes on the value 0. To see a more involved example, let's look at the multi-source shortest path program. Here I have written this program out using 2 lines of Dyna. Note, this program as written cannot be executed under a prolog or data log style of execution. Instead, it requires rexprs or something isomorphic to rexprs. Again, we have that the variable x, which is not present in the head of this expression, is going to have to be aggregated over, just like with the dot product example. Here the aggregator is min, which only keeps around the minimum value that is computed. This program is going to be combined with a number of edge weight facts, as I have shown here. Altogether, this program can be thought of as equivalent to the possible assignments of the variable start y and the result of distance start y as shown in this table. However, this program also defines a number of other values because of the second rule. Here, anytime the first 2 arguments are equal to each other, the distance is equal to the value 0. This is regardless if it was using an edge that we define or some other value such as foo or 3.14. So how do we represent this program such as shortest path? Here we have the base case for the shortest path, which is used anytime both arguments are equal to each other. We can represent this expression as a bag, where the arguments in the resulting variable have been mapped to this tuple of named variables, and we have the body of this rule represented as a bit of executable code. Note, I am temporarily ignoring the aggregator in this rule, but I'll bring it back shortly. Now, we can do the same for the recursive shortest path rule. However, if we just do the same as the above line, this ends up being somewhat awkward. We really need some way we can build this expression up. So let's try this again with the second rule. The first step is to normalize all of the arguments and the result variable name. Then we can start translating this program one term at a time. First, we are taking the call to edge and translating it into an R expression. We introduce new variables which correspond with any intermediate values that exist in this computation. We do the same thing for the recursive call to distance. For the plus expression, we introduce a call to the built-in plus operator. We then intersect all of these expressions where they're joined when they use the same variable name. Altogether, this expression is over the 6 variables, arg1, arg2, result, e, d, and x. So we use a projection operator to remove the local variables, which sums the bag's multiplicity for the given assignments for each of these variables. Now this expression is just over arg1, arg2, and result. So how do we introduce aggregators back into this program? Well, we introduce this directly into the R expression. It wraps the R expression that we have seen from the previous slide. There is a variable that is introduced which identifies what value is getting fed into the aggregator, just like with the projection. And here we also mark where the final result of the aggregation is going to be stored. So now that we have aggregation, let's show what the representation of the shortest path program is altogether. First, we normalize both of these rules such that they are over the same variables, arg1, arg2, and result. Here we have the conversion of the first rule, and here's the rule from before, the second rule from before. And now we take the union of these 2 expressions. Now wrap this entire expression in the aggregator, which is going to select the minimum value that is assigned to the variable min input for a given assignment of arg1 and arg2. All right, so now I'm going to talk about how we manipulate and rewrite these expressions to execute our programs. So our rewrites are designed to be semantic preserving and to simplify the expression. Our rewrites are non-deterministic, as there may be different rewrites that could be applied at any point. We are okay with any order of rewrites, even though this may give slightly different answers. Our system is fair between any of the available rewrites that we can use on an expression. This is important as a recursive program might not terminate if the system was unfair. And all of our core rewrites can be found in the paper. To illustrate the core idea of our rewriting system, we start with some small examples involving built-in expressions. Here we show the built-in plus operator, which operates over 3 variables and maps these variables to the bag of triples that corresponds with addition. Our system is looking for simpler expressions that correspond with this bag. So here the first 2 variables have been assigned the values of 1 and 2 respectively. This means that the only value that the variable z can take on is 3. So we have performed that rewrite here. This rewrite is semantically equivalent to the original expression and can be considered simpler as we can directly read the value of z. Now in the case that we have 2 variables unbound, such as y and z here, there are no rewrites which are possible, as this corresponds with the entire set of assignments to y and z. To eventually rewrite this built-in plus, we need another conjunctive rule to determine that z is equal to 3, in which case we can propagate the value 3 to any place where the variable z appears. Here we are showing that built-ins can support multiple modes, In this case, by having two of the three variables bound, we are able to perform a subtraction and determine that the value for the variable y is 2. By leaving this expression unrewritten when there is not enough information and being able to run the built-ins in multiple modes, this nearly gets us to constraint logic programming. Finally, to complete this picture, in the case where all of the arguments to built-in plus are known, we're able to simply check if the assignment is correct. This expression is rewritten as 0 or 1 to indicate that the multiplicity of a given assignment has in the bag at the top of the slide. So let's work through the shortest path example. Here we start with a query to the program which is written as an R expression. We then combine it with its definition of the shortest path that we had from a few slides ago. When combining these two, we rename the variables result arg1 and arg2 to match our query and substitute in the constants a and c. We now apply the rewrite rule to check that the two constants are equal to each other. Because they are not equal, this is written as 0, representing an empty bag. We have that an empty bag intersected with any R expression results in an empty bag. And we have that the union of an empty bag with an R expression results in the same R expression. Together, this simplifies the expression as follows, where we have removed the first disjunctive branch of this R expr. Now we're going to continue with this rule. We again look up the definition from edge rule from the program. And we rewrite this expression for edge, substituting in the variable e, x, and the constant c. Now we're going to check the equality between the constants d and a, b, and c, where only the last one is equal, thus rewritten as a 1. This corresponds with a bag where all the assignments to other variables are given multiplicity 1. We can now use the multiplicative identity of 1 times r is r, and now we get a simpler R expression where only the matching branches of edge remain. Now we propagate the value of x and e as they have been bound to constants. This allows us to remove the two projection rules for these variables. The system would continue doing rewrites on this new expression, just like we have seen so far. So the rewrite steps that we have seen so far probably don't seem too surprising, but we didn't quite make it to seeing the aggregator itself running, and it can take quite a few steps to see it do anything interesting. So I'm going to just take a moment to illustrate our rewrite rules for dealing with aggregators. So here we have our min aggregator, where I have assigned the 789 to the input variable of the aggregator. In this case, we can simplify this expression by just removing the aggregator, as there is only a single value. In the case that there are two disjunctive R exprs, R and S, then we are able to split this into two different expressions where each is going to be aggregated over independently. This can be important, as it is possible that only one of the two R exprs can be rewritten and simplified. When combined with an aggregator that can stop early, such as logical OR, this can result in a significant runtime improvement. Here's the interesting rule. In the case that there are no contributions, meaning that that is aggregating over an empty bag, represented here by 0, then this does not rewrite as 0 an empty bag, but rather returns the identity element for the aggregator. In the case of the min aggregator, the identity is defined as positive infinity. Now this might seem a little strange compared to other relational algebras which include aggregation, but we can recover a more traditional view of relational algebras by filtering out the case where nothing was aggregated over. The reason for this oddity is it allows us to have additional flexibility, as exhibited by our second rewrite rule here, and others that are in the paper which are useful when dealing with infinite bags. Our exprs for us are the internal representation for dealing with Dyna and other logic programming. We have ongoing work to integrate memoization, forward chaining, and mixed chaining based execution strategies using R exprs and their associated rewrites. This is already in our implementation and should appear in a future version of this paper. We are also working on exploring different execution orders, much like a database query optimizer, to figure out the most efficient way to execute a program given the flexibility we have in different rewrite orders. And we're also looking into compiling the sequence of rewrites. So thank you. That's my talk. And if you have any questions.
Okay, thank you very much, Matthew. Sorry, because I forgot to ask you about the recording of the session before. So I assume you are right with that?
Yeah, that's good. Thank you.
Okay, perfect. So do we have any questions?